In the last video, we talked about the difference between Venlic and the aryl groups, and we said that neither one of these undergo substitution very well because of the delocalization that's at play, those strong negative areas that are inside of those groups, and it can't really get into that carbon because that carbon has some negatives that's associated with it. So I told you it hung out with the X's, and that's why the nucleophile runs away and it never comes back. Keep that in mind. If you see somebody out in the bar or at the club or at a restaurant and you don't want to talk to them, just make sure that you're friends with some of their exes. And I think that will kind of seal the deal. They'll never talk to you again. Okay, so there's one more thing I need to talk to you about, and that is another way that we can distinguish between SN1 and SN2. So especially for secondaries and benzylics and allylics. Because we said that both of these can all of these can undergo both SN2 and SN1. So I kind of told you a little earlier on that there is a trick that we can do in order to kind of nudge it and talk sweet nothings in its ear and say, this is the way we want you to go. All right. So again, imagine your friend sitting in a car on the way home from a date, saying, I just don't think he's right for you. I just don't think that he's good fit for you. I think he's got a lot of baggage. I just don't like the friends that he hangs out with. I mean, think about those conversations that could happen in a car, or her, right? Just think about those conversations that could happen in a car on the way home. Well, we need to be able to persuade carbons to do things for us. And this is one of the ways that we can do it. So if I am faced with SN2 and SN1 both happening in the world of secondaries, benzylics, and allylics. Again, you can't trust them. Sometimes they're going to cheat and sometimes they don't. How can I make sure that they do cheat? Well, I'll get a friend that's way more attractive than the person they're trying to date, and then I introduce them. And then after I introduce them, I hope that they forget about that other person that I don't want them to know anything about. Right? I mean, that's how we do this. We got to connive. We have to be connivers. And I'm trying to teach you how to connive here. All right. So in the world of organic, the way that we do it is that we pick out partners. So nucleophile partners. That's the secret here. So if I want carbon to cheat and I want an SN2 reaction to happen, I need to make sure that I need to bring into the picture and introduce my friend to the prettiest, most handsome, or sexiest, however you want to term it, person that I can. That means in SN2s, I need fully blown negative charges. That is what we traditionally see with the SN2 route. That negative makes them a really good nucleophile. That nucleophile and that good nucleophilicity, folks, that means that that carbon's going to forget about the person I don't want them to associate with. And they're going to focus on this negative piece right there. They're going to cheat. Maybe that's what I want them to do. And that's the way that I'm going to do it. So we need to pick out what we call very strong nucleophiles. And those strong nucleophiles are going to come with a negative charge almost every single time. Very easy to pick out. Now, what if I do want carbon to hook up with somebody, but I think that carbon needs to be on their own for a little bit? You know, I would really like for carbon to be single. I would really like for carbon to kind of realize what they want in life before pairing up with somebody else. So what I'm going to do in that case is that I'm going to maybe introduce carbon to people, but I'm going to make sure that they're not sexy. I'm going to make sure that they're not beautiful or handsome or whatever they find attractive. I want to make sure that they're kind of ugly, right? I mean, if I can introduce carbon to ugly friends that they're not maybe attracted to in any form or fashion, then I can persuade carbon to be on their own for a little bit, And then when the time is right, go in and allow carbon to introduce themselves to my more attractive friends. I know that sounds horrible, but that's the way it works. So the way that we do this is that we pick very weak nucleophiles. What are weak nucleophiles? They're things without negative charges. So OH, I'll put a hydrogen there. HOH, that would be water. NH2, I'll put a hydrogen there. That could be an NH3 group, right? The OCH3 group, well, I can put an H on that. Okay, and that would be something like methanol, CH3OH. So these carry no negatives, full-blown negatives, and they typically have a hydrogen where that negative charge would be. And that's the difference between SN2s and SN1 preferred nucleophiles. So if I bring in a strong nucleophile, I'm almost going to guarantee that carbon will cheat. If I introduce carbon only to very weak nucleophiles that are not very attractive, then that probably means they would be okay being on their own for a little bit, rearranging, getting their life together, and then later on hooking up with this water that they weren't necessarily attracted to in the beginning, right? But maybe after hanging out with them for a while, they realize they're not too bad. Or maybe that CH3OH group. They're not going to be attracted to that too much in the beginning because it's not full-blown negative. So carbon rearranges, carbon becomes single for a moment in time, and then carbon takes a second look at that methanol and says, you know, you're not too bad, I guess, in the very end. I think that I can deal with this. So you want to go and try a relationship together? You want to go out on a date? And that methanol is going to say, of course, that's what we'll do. So here's the lowdown. That's what I'm going to call the lowdown. A good summary of SN2 and SN1. With SN2, it happens in one step. The carbon cheats, brings the new partner in while kicking the old one out at the same time. Second order kinetics, which means the concentration of both the nucleophile, the incoming group, and the alkyl halide are important. Next, no carbocation rearrangements happen because it happens in one step. Wherever the halogen is, that's where that nucleophile is going to go. After that, we said the products have inverted configurations. Walden inversion has to happen because they're cheaters. They have to sneak through the back door. Always keep an eye out on the back door, folks. You never believe what goes on. So if it starts with R, it ends up with S. If it starts with S, it ends up with R. It's always the inverse. Reactivity order of the cheaters. Primaries first. It's the fastest because there's no neighbors. That can cheat much easier than secondary, which does have a neighbor or two. Benzylic and allylic come next. They're kind of identical. And they're only slightly more stable than secondary because of delocalization. And then tertiary, it will never really happen. There's too many neighbors around for you to actually cheat and get by with it. SN2 reactions, you need a good nucleophile, right there. You need high concentrations of that good nucleophile that is very negative. And you need to make sure that you have an aprotic solvent. And that aprotic solvent, again, we've talked about that definition. A solvent that does not have a hydrogen on an N or an O. If you can make sure that this is taken care of, you can guarantee that SN2 reactions are going to happen when you have a choice of what goes on. So for instance, primary, you have no choice. It's only one route. They're always going to be cheaters. Tertiary, you have no choice. They're always going to end a relationship before they start a new one. That's just the way tertiaries work. It's those freaking benzylics, allylics, and secondaries that cause you problems. Those are always the wishy-washy friends that you never know where their head is at. The same thing is happening here in substitution. But you can control it. You can persuade them to do what you want them to do as long as you give them a high concentration of a good nucleophile in an aprotic solvent. Next are the SN1 reactions. They are completely opposite, folks. Look at this. They happen more than one step. They are first-order kinetics, which means only the concentration of the alkyl halide is going to be important. That's it. Nothing more. Not both is required. Only one. That's why it's first order. Carbocation rearrangement is going to happen here. You always have to look out for that rearrangement because that can really do a number on you in the product side of the house. Next, products could be inverted, but products could also keep the stereochemistry that they have in the beginning. You just never know. You're going to get a mixture of all of it. The reactivity order here is completely flipped. Tertiary is going to be the best in the SN1 reaction. It's got a support system for that carbocation. It can stabilize itself out to be single for a little bit. Benzylic and allylic come next. Delocalization helps stabilize them. And because of that, they're a little bit more stable. They can hold the carbocation a little bit better. Then secondary, then primary. These SN1 reactions, you want to make sure that you have a low concentration of a nucleophile. So if you have a good nucleophile that carries with it a negative charge, you want to make sure that that is limit. You don't want a lot of it. Low concentration of a nucleophile. Or, folks, pick a poor nucleophile. You want to pick something that has no negatives with it. That's going to be the best way to drive an SN1 reaction. Give it something that it's not attracted to in the very beginning. Then after some time, after they go out on a date, after they get acquainted with each other, then they can think about dating. Otherwise, it's just a one-night stand. And if you want to make sure that SN1 will happen, you need to make sure that only ugly things can get to it. So make sure that you only introduce these to the workplace. Make sure it only goes into a protic solvent. That way, the attractive ones, people are going to beat you out to it because everybody's attracted to the most attractive one out of the bunch. Imagine you in an office, in cubicles, and there's one pretty person in the corner of the room. Everybody's going to gravitate toward them. Right? And you want to be professional about it. So you're not going to be, all kind of tipsy, going up and trying to make the move, right? You're going to have a little bit of ground behind you. The protic solvents will ensure that your attention will be turned to other things in the room, like the person in the cubicle next to you, versus the person all the way across the room that's a little bit more difficult to get to. So low concentrations of a nucleophile, or pick a poor nucleophile and make sure that you do it in a protic solvent if you really want to ensure that SN1 is going to go forward. Something else I want to talk about too before we do some more of these example problems, it's just something I'm going to mention. You will never probably see a question with bifunctional molecules. What does that even mean? Well, bi means two, and functional means two groups. So these are groups or molecules that have two groups on them that can actually do something. We're often just concerned with, hey, here's a halogen, and that halogen can be replaced, and blah, 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 blah. But sometimes you've got multiple functional groups in the same molecule that can react together. They can react independently, but they can also react together. So two different things can happen here. A intermolecular reaction where a molecule reacts with the same molecule. All right, so that means here I've got a molecule, here I've got a molecule. They're identical, like identical twins, and they go hubba hubba. I mean, can't you imagine? I guess each their own, but there you go. These two things are going to make a product baby, and they're twins. You get what I'm saying? Next, molecule reacting with itself. Oh, God. Oh, God. Where's he going to go with this? Molecule reacting with itself. That means that I've got a molecule here, and it's got maybe more than one functional group on it, and it doesn't need anything else. It doesn't need a partner. It's very happy with itself. You get what I'm saying? This is an intramolecular reaction. So that means it's going to take one piece of itself and another piece of itself and do hubba hubba there, and we get a product baby that forms after it. Well, that can be a completely different product. So let's take a look at some of these, and let's do the intermolecular version first. So notice here is a molecule, and this molecule has a bromo group on it, but it also has this oxygen-containing group as well. So if it's nearby a twin, it might say, God, you're good looking. I mean, I stare at myself in the mirror, and then I see my twin, and that's as good looking as me. So, hey, you know, you want to get together? That's what's going on here. Oh, could you imagine? So what's happening is that the oxygen from this molecule is actually negative, is actually reacting with the carbon that wants to be a cheater. And then that's kicking off the bromine. So we actually see a hookup, a big, huge hookup between these two molecules, and those two molecules are identical. There's no extra reagent that we have to put into the system. That's how these are a little bit different. Notice there's no nucleophile that we added in. That's just the way that this is going to be. So again, you're not going to see a lot of these. I don't even think I asked them too much on the test, but you might see a quick little question about it in Blackboard or some type of online assignment, and you at least now kind of know what an intermolecular reaction is. Two molecules, identical, multiple functional groups, and because of that, one group looks a little prettier than the other one, and they begin to react with themselves. Now, the next one is the intramolecular, which doesn't need nobody. That molecule's perfectly happy on its own. That molecule can take that oxygen, and it says, I can satisfy my need with me. I don't need nobody else. And that's what this molecule decides to do. So it actually will bend around, and it will connect with that carbon, and that carbon decides to make that halogen leave. And when it does that, look, folks, I mean, it forms kind of a circle. It forms a ring. And it really just depends on how many carbons there are in that mid-step and how easy can it form that ring. We notice that, you know, four-membered rings are less stable than five. Five are less stable than six, and so forth. But it can wrap itself around, and that is what we call an intramolecular reaction. Here are a couple more examples of intramolecular reactions. So here's the compound all the way around. It's kind of drawn that way just to kind of prove it to you a little bit easier. That carbon has a chlorine. That's a halogen. It's a very good leaving group. It's ugly. And then that carbon's going to look and say, gosh, I am so gorgeous. Look at this piece on me. And then they're going to look at that oxygen and they're going to say, I think I am just totally fine. As long as I have that going for me, that's all I need. I don't need nobody else. So that oxygen turns around and it connects to the ring, and it makes this ring structure. And it just kicks off that chlorine. It says, I don't need that. I don't need this relationship. I am the only thing that I need. That's what intramolecular reactions are. Same thing's going to happen here at the bottom. Here we have basically a carbon chain, and on one end of the carbon chain I have a bromo group, very ugly. I mean, it's not doing anything for me as far as a relationship goes. I'm kind of depressed with it. But looking at myself in the mirror, I'm going to go, that's hot, right? And then I look at this nitrogen group. That nitrogen group is a very attractive group. And I'm like, why am I going out to all of these bars? Why am I going out to all of these clubs trying to find something when all I have is right here with me? So a connection happens, and we call that an intramolecular reaction. And we get a circle that happens because of it. Now, where do those two methyl groups come from that are down here? Folks, don't let that throw you off. There's two NH3 groups on that nitrogen. So it still forms the ring, and that bromine, poop, goes off, and we'll never see it again. All right, so that's where this video is going to stop. In the next video, we're going to focus on just example problems, a little bit more of them, and we're going to juggle a little bit about SN2 and SN1 around as well. So before I stop the video, though, here's the example problem that we're going to come back to. So it says, what nucleophiles would form the following compounds as a result of reacting with 1-iodobutane? So they want you to take 1-iodobutane, and they want you to predict what you need in order to make these products that you're seeing on the screen. A, B, C, D, E, and F. So take a stab at them. See what you come up with. What nucleophiles would you pick in order to make this work? And then press play on the next video and double check your answers and see if you're going to be correct. I hope you are. I think these are pretty easy. I hope so, at least. If not, I didn't do my job and you didn't do your job either. I'll see you in the next one.